Our next section is going to cover orbitals and the shapes of those orbitals. Last time we talked about the quantum number, and we called it n equals 1 or n equals 2 or n equals 3. And these were concentric circles leading away from the nucleus of increasing energy, right, which is what we see over here on the right side. We're now going to call this the principal quantum number. We're still talking about hydrogen. We're going to call this the principal quantum number, the first quantum number, and we're still going to call it n. But that is, it's going to matter again here in a moment, maybe a little bit more than just what we saw in the previous set of notes. But this indicates the relative size and energy of atomic orbitals. So if n equals 1, right, it's closest to the nucleus and it's the smallest. It's also the lowest in energy. Okay, n equals 2 means it's going to be slightly bigger than n equals 1, and it's going to have more energy in it. Okay, and n equals 3 even more energy, but the same shape, depending on the shape of the orbital, which we'll see here later on, but more energy to it. As n increases, the orbital becomes larger, the electron spends more time further from the nucleus, and the atom's energy increases. So again, you're farther away from the nucleus, it takes more energy to stay there. N specifies the atom's major energy level, okay? So these are major energy levels. We call them, again, the principal quantum number. N equals 1 is the lowest energy level, that's the ground state. You can go all the way out to n equals 7. Theoretically, you can go beyond that, but n equals 7 is the last real one. Okay, so each of those principal quantum numbers from 1 to 7, they contain energy sublevels. And for whatever number it is, that's how many sublevels there are. So, for instance, n equals 1 has 1 sublevel, n equals 2 has 2 sublevels, n equals 3 has 3 sublevels, and so on, right? So they're kind of broken up as you keep fanning out from the center, which is kind of what's going on down here. Okay, so what do these sublevels look like? Well, sublevels are labeled as S, P, D, or F according to the shape of the orbital. So there's S, P, D, or F. There's 4 different shapes here. S are going to be spherical. Okay, they look like this. P are going to be dumbbell shaped. They kind of look like sort of almost like an hourglass, right? 2 bulbs on each side here. And one along the X, one along the Y, and one along the Z axis. And then D and F orbitals have more than one shape. You can kind of see what they look like down here. They start getting really complicated, okay? But the n equals 1 level has only got one type of orbital. N equals 2 has 2 types of orbitals. N equals 3 has 3 types of orbitals. So we'll see how this all plays out. Okay, so at the n equals 1 principal quantum number, there's only one sublevel. And there's only one shape of orbital, and those are s orbitals. They're spherical, right? So you have a 1s orbital is what we're going to call this, okay? We call it a 1s orbital. That's the lowest energy possible. 1, n equals 1, meaning closest to the nucleus, and s, meaning spherically shaped orbital. Okay, so it will look like this. Electrons in this sublevel are designated as 1s, again, lowest energy level possible. N equals 2 sublevels. Well, there are 2 sublevels here for the principal quantum number of n equals 2. You have s orbitals and p orbitals. Okay, so here are those dumbbell-shaped p orbitals. It's kind of what they look like. This time around, right now, you'd have a 2s orbital. Notice it's the same shape as a 1s, but it's now further away from the nucleus. Okay, so it's at a higher energy level. We also have the 2p orbitals. We have the p, x, y, and z orbitals. So this one would have at the n equals 2 level, right? We've got 2 different types of shapes. We've got s and p, and we have 1, 2, 3, 4 different possible orbitals that these things could end up with. Again, this is just illustrating the difference between 1s and 2s. 1s is the lowest energy level and spherical, and this can only happen if you have n equals 1. And 2s can only happen if you have n equals 2. Okay, same shape, further out, higher energy level. If n equals 2, we can also have p orbitals. Okay, we can have px, py, and pz. They're sort of dumbbell-shaped along each of the axes. We haven't seen this one yet. These would be d orbitals. This is if you get n equals 3. We've got 5 different shaped d orbitals. Notice they kind of lie along planes on a 3-dimensional axis, and they're also dumbbell-shaped, minus, of course, this last one here, which falls along the z-axis. But this is what the shape of d orbitals would look like, and this would only happen if you have the principal quantum number n equals 3. So where is the electron in a hydrogen atom? The electron can only occupy one orbital at a time. There's only one electron. If the hydrogen atom is in the ground state at its lowest energy level, no energy has been added to it at all, that electron is going around the 1s orbital. So if you want to think of it, right, here's your nucleus, here's your 1s orbital, okay, going around it. If you want to think of it as spherical and three-dimensional, we could think of it like that if you wanted to. Okay, maybe that might help give you an idea here, but it's traveling around the nucleus in the 1s orbital. Lowest energy. When it gains energy, it can occupy any of the vacant orbitals above it. So the next level up, right, if it gets enough to jump to the n equals 2 level, okay, it could occupy then the 2s orbital. Okay, apologies for the bad drawing here, but I'm doing the best I can. Right, that would be the 2s orbital. It could also occupy any of the p orbitals, right? So you have the one along the x, y, and z axis, right? Okay, I'm doing my best to try to draw them on there like that. It could occupy any of those. So this, 2px, the 2py, and the 2pz orbitals. It could be in any one of those if n equals 2. Okay? In any of these orbitals, I know hydrogen's only got one electron, but if we start getting to more complicated atoms, each of those orbitals can hold a maximum of 2 electrons. Basically, what ends up happening is once you've got 2 electrons in there, you can't put in any more negative charge because things would just start to fall apart. So for the first 4 levels of hydrogen, here's what it looks like. If you have n equals 1, the only type of sublevel possible is S. Okay, you've only got one possible orbital there, and the total number of orbitals related to the principal energy level is 1. If n equals 2, you can have S and P shaped orbitals. There's one S, so there'd be 2s. There are 3 2p orbitals, again, the 2px, 2py, 2pz, for a total of 4, okay? And then for the principal quantum number n equals 3, we have s, p, and d orbitals. S is 1, p is 3, and d is 5. That gives you a grand total of 9 orbitals, okay? For n equals 4, we got s, p, d, and now f, which will give us 1, 3, 5, and 7. So you can kind of see the patterns forming in each of these, which would give us a total of 16, right? And if you've been kind of following along here, this would, since we said that each orbital can hold a maximum of 2 electrons, well, that would be 2 electrons for the first one, right? There's only 2 electrons that can fit there. This one would give us a total then of 8 more, right? And this would give us 18 more, and this would give us 32 more. We're going to see kind of how this plays into the formation of the periodic table here in our next section.